Okay, for those of you that were here on Wednesday, we covered quite a bit of stuff actually. We began our first rotational dynamic problem. Okay? Alright, so get out your notes. Your notes.
Yo notes.
Your notes. The notes. We're gonna get cranking today. Okay, so here we go. Now we know that we have translational motion.
Wait, who's we?
Us. You know, we, not them.
Yes, in friendship or we?
All right. In translational motion, we have translational kinematics. Okay. So we have, x equals x naught plus v naught t equals 1 half at squared, and all those relationships between displacement, velocity, acceleration, and all that, right? And then we also have F equals ma, which we split into two perpendicular directions so that mathematically we can handle it with algebra. And normally we split it up this way, F equals ma in the x direction, and F equals ma in the y direction. Okay? Or we can split that up into any perpendicular and parallel direction if we want, perpendicular to the acceleration and parallel to the acceleration. Or we've got one other option now, and our other option is that sometimes we will have both a centripetal and a tangential acceleration. So in the most general form, we'll split it up like this. F equals ma for the tangential acceleration, and F equals ma for the centripetal direction. Okay?
We do this energy tree like every year.
I know.
I've never seen it before with a test.
You like these?
It's like Christmas.
I've never seen this. In October.
Christmas in October. All right, so we kind of have this hierarchy of types of problems or types of situations, okay? And we like to set it up like this, so hopefully that this one right here is 0, we hope. We want to put smiley face next to that one. That's what we like, okay? That the perpendicular acceleration is 0, right? Okay, now we have rotational motion. And in rotational motion, we have our rotational kinematics, which is theta equals theta naught, and all those theta, omega, alpha, all those graphs, all those integrals, all those differentiation relationships between angular displacement, angular velocity, angular acceleration, and time, right? So we have all those things. But now we have a new one, the rotational equivalent of F equals ma, which is torque equals I alpha. Okay? Now, this one requires us to think about things a little bit differently. Remember, in translational motion, all we considered was motion of center of mass. That's it. The motion of the center of mass, and that's it. We didn't really care where the forces were located as long as they pointed in the right direction. Piece of cake. Okay? Over here, we've got a little bit more of an issue going on. Because now we have torque, and torque is R cross F, and you want me to write down all the variations of that as well?
Always.
Sure.
All right.
Actually, yes.
RF sine theta, which is the same thing as RF perpendicular to the radius, or R perpendicular to the force. Okay, any one of those. Okay, however you want to think about torque, whichever one is the most convenient for you at the time. Okay? So where the force is located makes a huge, huge difference. And then where the mass is located on the object makes a huge difference for our rotational mass, or rotational inertia, or what they call moment of inertia, okay, which is integral of r squared dm. So we either have to calculate it this way, if it's a continuous shape, if it's a lumpy shape where there's discrete pieces of mass located certain places, then it's the sum of the mr squareds. Or you can memorize certain shapes, and these are the shapes you must memorize. Remember we have, what are the shapes? Okay, we got
This.
hoop, disc,
Solid sphere.
sphere, sphere both solid and hollow.
And a bar.
And then a bar in the middle and a bar at the end. Okay? If you've got those, oops, I shouldn't have put center of mass on this one. That's not the center of mass. No wonder that looked weird. There we go. Rotating about that point instead of free rotating about its center. Okay? Now, those you have to have memorized. Okay?
What are the ones who put this sphere in?
Do you want to know what they are?
Is that I equals M
All right. For the hoop, it is,
I equals
MR squared.
it's mr squared. For a disc, it's
1/2.
1/2 mr squared. For a sphere that's solid, 2/5 mr squared. For hollow, 2/3 mr squared. For the bar in the middle,
112.
112 mr squared. And for the bar at the end, 1/3 oops, I did r squared. Back up. That's ml squared and ml squared right there. Length, because there's not really a radius. It has no radial geometry, so we just use length. All right. Then we also know that since this concept is a scalar concept, we can take any strange object we want, like this, with a sphere attached to the end, and if we rotate it right here, then what we can really do is take this object like this and add it to this object out here, rotating about this point.
Parallel axis theorem.
Okay, now this one we don't need parallel axis theorem. This one right here, if this was a, say, a solid sphere, okay? So, and this is a bar, and this is a solid sphere. So this one right here would just be 1/3 ml squared, where this is L. And let's say that this right here is R, just to make it easy. Okay? So the moment of inertia about this piece right here is going to be
2/3. No, that was all. Yeah, 2/5.
2/5 ml squared, but it's,
MR squared.
oh, thank you, mr squared. Okay? But that's if it's rotating about that point, right?
But then you have to add it to.
Yeah, then we have to transfer it from here to here.
So it's R plus
So it would be, parallel axis theorem is this plus an m, yeah, whatever this is right here. In our case, it's going to be, well, what would it be?
L plus R.
L plus R. L plus R squared. And I'm assuming the mass of this is m and the mass of this is m to make life simpler on us, okay? And you would add this piece plus this piece plus this piece all up to get the total, okay?
It's like that pendulum problem.
Yes. Which pendulum problem?
Taken from the
Last year homework.
Oh, last D homework. Yes, exactly right. Exactly right. That was,
Wait, what's this?
in fact, that was the problem, just to figure out the moment of inertia of a pendulum, right? All right, so there you go. Now, all of that is just set up for being able to figure out this problem right here. Okay? So let's solve our first one. Those of you that were here last time have already seen this, but it's a good one to redo. Okay? Let's say I have a pivot point right here. Let's say the length of this thing, I don't know, let's make it L. Let's make the mass here M, just so our first time through. And it's pivoted right there, and at that instant I let go. Okay? Just at that instant I let go. So it's going to fall this way. Okay? My question is at this instant, what's the moment? At this instant, what's the angular acceleration? Okay. So, when you see a problem like this, where something is rotating, and the force is causing rotation, then we got one of these. Alright? So let's take a look at it real quick. The sum of the torques equals I alpha. Alright. What goes here?
R cross F.
Okay. R cross F. What is our radius? Well, first of all, what's our force?
mg.
Right here, we've got an mg. So our force is mg. What's our radius?
1/2 L.
L over 2. What's our sine theta?
1.
90 or 1 half.
We have this situation here, right? This one or this one, whichever one you prefer. We are perpendicular, right? So our force is already perpendicular, so we're in business. So I'm going to write it down anyway, just so you see it. Our sine theta is 1. Okay, moment of inertia of this thing.
1/3 ml squared.
Alpha. Alright, so just like we build F equals ma, this one's a little harder to build because we have multiple torques equals moment of inertia times alpha. Alright, from this point on, all we do is cross stuff out and cross that one out. And we end up with, I believe, that alpha equals, what was it, 3/2 G. Oh, I got an L here too.
Over L.
Over L, thank you. 3G over 2L. All right? First of all, what does that mean?
That as the bar
It's
gets longer, the less acceleration it has. The smaller torque.
As the bar gets longer, less angular acceleration. That's true. I didn't even think about that. That wasn't even what I was looking for. Nice. We have new learning. Yay. Go team. All right, now. That is true. I didn't think about that. As the bar gets longer, our angular acceleration goes down. First of all, are our units correct?
Yes.
Meters per second squared divided by meters gives us nothing per second squared, which is radians per second squared, right? Okay, so angular acceleration in radians. Okay, but that means that it wants to accelerate angularly this way at this rate. Will it stay this angular acceleration the whole time?
No.
Okay. If it's in this position, how does it change?
The angle between the bar and the force.
Okay, the radius doesn't change, the force doesn't change, but the angle remains now, right?
Yes.
The angle remains. And so our angular acceleration, our acceleration will change with angle.
So will you?
That's Elmer Fudd up here today.
Debit season. Wedding season.
That's right, Webbit season. All right, so it will change with angle. All right, and when it gets down to the bottom, it will be zero angular acceleration. Now I'm going to say it all day. Okay, what's the linear acceleration at, say, this point here in the end? How do we figure that out?
A equals alpha R.
Okay. linear acceleration equals alpha times r, right? And our alpha is 3g over 2l, and if our r is at the end, L cancels, and we're left with an acceleration that is 3/2 g. Whoa, 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 whoa. Does that disturb anyone?
Feel disturbance.
It should disturb you a bit.
It's greater than G.
It's greater than g. What the heck? It's greater than g.
Yeah, G.
Why is it,
Whoa! Not if what?
why is it RL over 2?
All right. This means that the end of the meter stick, if you hold it and drop the thing,
So,
if you hold it right here and let go, that the end accelerates downward faster than if I just dropped it. Doesn't that violate some sort of physics?
No, good.
You're like, eh, whatever. We don't care. Yeah.
Wait, no, because it shows centripetal acceleration.
RL in that one.
Because I was looking for the end, the acceleration of the end of the bar. So I'm looking at the acceleration right here. The acceleration here, let me draw that bigger because that looks too small. All right, the acceleration out here is 3/2 g. What's the acceleration here?
0.
We have no acceleration here. Acceleration equals 0. What's the acceleration of the center of mass?
G.
Really?
No, it's gonna be half of 3/2, 3/4.
It's going to be half of 3/2. Because this radius now is L over 2, which gives us 3/4 right here. So it's going to be like that. And notice it's going to have a linear relationship from 3/2 g down to 0. Okay? Now, here's the deal. The sum of the forces equals ma still works for an object that is rotating. But what point on the object are we interested in? Center of mass only. That's all this tells you about. It's the center of mass. That's it. So, this little business right here, that the end is falling faster than 3/2, falling faster than g, or accelerating faster than g, does not violate any physics because it's the center of mass that makes the difference. Okay, so let's just look at this from F equals ma. At this instant right here, when we're horizontal, there's no x motion, right? So all we have is y motion. What does this equation tell us? What are all the forces acting on this thing when it's in this position? We've got gravity, and what else?
The vertical force at the
We got a vertical force right here, V. Is V equal to mg?
because it's accelerated.
Okay, now look. Is the center of mass, if I drop this one end like that, is the center of mass accelerating?
Yes.
Yes.
Which way is it accelerating?
Towards the truth.
Wait a minute. At this instant, when I just let go, is it moving? No, right? So if it's not moving at this instant, then it has no centripetal acceleration. Right as I let it go, which way is it accelerating? Just straight down, because we have no force inward. So let's look at this. That means that this right here, if I call down positive, I get mg down minus the vertical force equals ma. And remember, I'm interested in the center of mass only. Do I know what the acceleration of the center of mass is?
Yes.
I do. What is it? Is it 2/3? I mean 3/2?
No.
It's 3/4. So I put 3/4 in here. Did everybody catch that? 3/4 G. I need to put in the center of mass location to figure out what my acceleration is for my center of mass. Okay? Does my M go away? My M does not go away. So what's V?
V is mg minus 3/4.
It's 1/4 mg. Okay? 1/4 mg.
So it decreases.
So say it again.
It decreases.
The vertical force, yes. Now look. Where do I have it this way? All right, right like this. Okay, when I let go, when I hold it like this, then both my fingers hold upward equal to 1/2 the mass, right? Then when I let go with my right hand, and it rotates this way, as soon as I let go, the force that my left hand has to exert drops from 1/2 mg to 1/4 mg. How does it know? Yes.
Don't we have to carry through with our sine theta? If
Now, I'm just talking about this one spot, right? So, we'll get to that sine. I'm going to put the sine theta back in just a second, okay? So, the force that I'm holding up with is equal to half the mass, and then when I let go with this hand, the force actually drops in this hand, okay? It actually goes down, and the object accelerates downward, dictated by this, due to the acceleration of the center of mass, okay? That makes sense. By the way, we didn't answer. How does it know? How does my left hand know? Because it's smart.
It's not cute.
I mean, why doesn't it? What's that? Yeah, that's not cute. Like if it was held up by, it was pinned to the wall or something. How would the wall know? It does know. Yeah. How does water know to roll downhill?
Gravity.
Gravity.
That's the only answer that's.
Because the forces tell it to, right?
Yeah.
Okay. So like if you have this thing attached to the wall to a pivot, okay, and you let go with this end, the wall's force on that pivot will drop from 1/2 mg to hold it up down to 1/4 mg because the forces tell it so. Because of the motion of the object and the interaction between all the atoms tell it what to do. Okay? That's how it knows. All right? Okay. All right, so let's add our sine theta back in. What would this answer look like if we left our sine theta in so that we could see what the force looks like as it moves? Then the sine theta stays. Sine theta. And then our answer over here will have a sine theta in it. So our acceleration is then that, correct? And when theta becomes 90, this becomes 0, right? When it's in this position, there's no longer any angular acceleration, okay? Because the radius is this way and the mg is this way, so radius and our mg is that way. The angle in between them is 0, and so you get sine of 0. I'm sorry. Yeah. Sine of 0 is 0, right? So I had brain fade for a minute. And then we go over here. What does our acceleration of the center of mass look like then? Then instead of it being 3/2 g over L times L over 2, there's a sine theta in here, right? So we have a sine theta here. Okay? And notice once again that linear acceleration goes to 0 when we reach the bottom. And so what's our vertical force going to be like? There's a sine theta here, right? So our vertical force as a function of theta, okay, becomes mg minus 3/4 mg sine theta, or mg 1 minus 3/4 sine theta. Does that look right? Okay, so our vertical force varies. Okay? All right. Now our vertical force, this is not going to be the complete answer for our vertical force. Somebody know why?
Principal acceleration.
Yeah, because this does not give us the complete answer for our vertical force because it's moving as it comes through here, right? So it's moving. So we really need to add another component to that because there is some centripetal acceleration. This is the vertical force just due to the tangential acceleration. All right? So vertical force only due to tangential acceleration. There's a centripetal acceleration going on at the same time. Okay? That's a little farther than I want to get right now. Okay. Okay. I think that's where I want to quit on that one. Okay. We need to talk about let's work a couple problems. Okay? Leave this stuff over here. Okay, this is like a bicycle wheel. All right? This is like a bicycle wheel. Okay, you know what a bicycle wheel looks like, right? With spokes and everything. Where's the vast majority of the mass? On the outside edge. So we're going to model this as a hoop or a ring. It's not really, but we're going to model it as such. Okay? All right, the inside radius is approximately 7 centimeters. The outside radius is about 35 centimeters. The mass of this bicycle wheel is about 2.4 kilograms. We're going to assume it to be a hoop. Our hoop is our assumption. And let's say the force on the chain, this is the chain right here, is which is pulling on the gear. This is the gears right in here. This is the wheel out here. The force is, what do I have it, 18 newtons. Not a tremendous force. And let's say it starts from rest. Okay? All right. First thing, part A. Find omega at 5 seconds. And then part B, find theta at 5 seconds. And then part C, how many revolutions after 5 seconds? So how many revolutions has it made after 5 seconds? Where's theta? Where would theta be?
Just anywhere.
Right.
Anywhere?
It's just the angle.
Maybe between R and F it will be 90.
If this is omega, what's omega?
Velocity.
Angular velocity, then what's theta?
Angular.
Angular displacement. So that would be, what's the angular displacement of the wheel because of the force on the chain and the gear making the wheel turn. So it would be like asking how many revolutions, except I'm asking how far did it rotate in radians here, right? All right, so how many radians did it rotate? We'll quit there for now. So, all right, go. We're looking for omega. Okay, look, with the information that's given, we know that V naught equals 0 from this, and we also know, everybody, and this is really important, when it starts at rest, we know omega naught is 0. Okay, we're looking for omega. Well, how the heck do we find omega? But this is alpha. Okay. Now, remember that in order to find omega, or velocity, a lot of times we have to find the acceleration first, right? So we're looking for an angular velocity, so let's find the angular acceleration through torque equals I alpha. Okay, do we know the torque?
Yes.
Sure, it's R cross F. Or for us, R is 7 centimeters, 0.07 meters. And our force is 18 newtons. Do we have to worry about the sine theta?
No.
Okay, no. I'm going to put a little perpendicular sign here because we're in good shape. I'm going to get rid of the cross. So there we go.
Why don't you use the outside radius?
Okay, why didn't I use the outside radius?
You can use it if you want to.
Could I really?
No. What? I don't know.
What are you talking
Wait,
about?
why did you?
For the F?
It's because the force is. I guess
No, the
attached
force
to
is
it.
the force is
Okay, the
rotating.
force
The force
is
is little
here.
center.
Yeah.
So I have to use that radius. Now that's really important because sometimes they'll give you multiple radii and you have to use the correct one. All right? Okay, moment of inertia times alpha. Our moment of inertia for us, though, is
MR.
mr squared. Now in this one, our mass is 2.4 and our radius is this time 35, right? That's the radius to where our mass is. So 0.35 meters squared alpha. So we can find alpha. Alpha turns out to be, I got 4.29, is that right?
Yeah.
Rads per second squared. Once we have that, how do we get omega at 5 seconds?
Omega equals alpha t.
Omega at 5 seconds equals what? Omega naught plus alpha t. Omega naught was 0, so hey, this is easy. 4.29 times 5 seconds.
21.4.
21.4 rads per second. Don't forget your units, everybody.
They're non-existent.
They will really be mad at you if you don't remember your units. Okay, how do we find alpha? I mean theta then at 5 seconds.
1/2 alpha t squared.
1/2. Oh, yes. Technically, it's theta equals theta at 5 seconds equals theta naught plus omega. Almost wrote v. Omega naught t plus 1/2 alpha t squared. But I'm going to assume it starts at 0. And I'm going to assume that it starts at a 0 velocity, angular velocity. Okay? So I get 1/2 alpha, 4.29 rads per second squared, times 5 seconds squared, giving me a grand total of 53.6 rads. Okay, I hate rads. I don't know what a rad is. I don't know how many 53.6 rads is. It doesn't stick in my brain. So I want to know revolutions. How many revolutions is that?
53.6 over 2 pi.
Okay, the conversion is I take this and I know that if I have 2 pi rads, then that will be 1 rev, right?
Yes.
I divide by 2 pi, and I get something that makes more sense to my little brain.
8.5.
8.5 revolutions. Okay?
All
All right.
Did you put it into parentheses? No, I didn't put it. Yeah, you need to put it in parentheses always.
All right, now I want to know how far that bike would have traveled.
It costs points on the homework.
Now, obviously it's a simplified problem because I do not have any friction on the tire or anything like that. Because there would be more than just this one force if this was a real bike, right?
So how would friction, where would friction,
Friction
Good
would
question.
would that be in
outside.
the,
outside.
Well,
Or would it be an inside?
there would also be
The friction would be here along the road.
We assume it's a friction thing.
Yeah, we got a frictionless surface. So how far does the bike go? Zero.
Oh,
All
that's
right.
a good question.
Because it's frictionless. I'm not going anywhere.
Everything is zero.
All right, so neglecting the fact that we didn't put any friction in here, this is an imaginary bike, right? How far would this wheel travel if it went through 8.5 revolutions?
that times the circumference?
Time to the circumference.
Okay, that times the circumference, right?
Yes.
2.
So would this be like part B or part B? Do we just answer and we do part 6?
What's that?
Part B, do we just answer? And
Part B, you just answer it in rads. So this is our answer to part B. This is our answer to part C.
35 centimeters including the end.
Technically, you know what? Technically, Alexandria, you could answer it either way for this one because both of these are the same statement. If they just ask that, you could put it in this answer if you want. This is the first answer that popped out of the equation. Sorry, this is the first thing that popped out of the equation. So I would just put that down. But if you don't like that and want to put this down, that's okay. It's like answering something in either miles or kilometers. It's the same answer. It's just a different unit. Okay? All right, so we have two options to figure out how far this would have gone. X. Now, if this bike tire rolls 8.5 revolutions, then I could take the 8.5 revolutions and just multiply times the circumference, which would be 2 pi r,
7 pi.
which 2 pi r is 0.35 meters, right? And what do we get if we do it that way?
That's 7 pi.
18 point what?
18.75.
Okay, 18.8-ish, 18.8 meters, right? Okay, there's another way to get this as well. The other way to get this is to realize that, look, I can relate theta to x, okay? I could have just taken theta times r and would have gotten the same answer, which would have been 53.6 rads times
Wow.
radius, which is
Forgot about that
0.35
one.
meters. This is actually a little easier,
Yeah.
and that will also get you the answer, right? Now, this is only true, in fact, both of these are only true if the bike tire does not slip as it rolls. Like we said, if it's on ice, you can have as many revolutions as you want, but if it's slipping relative to the ground, you're not going anywhere, right? So this should give you the same answer. Okay? All right. So what's the velocity of this tire after 5 seconds?
Do we want to know?
Sure we do. We want to know because I asked.
Hold on.
7.49.
Oh.
7.5?
Well, the easy way to do it would be just changing x over changing time, right?
Uh-huh.
Should be 18.8 over 5, which gives us, what is it?
3.7. Yeah.
3.7 meters per second. Okay, but I got another way to find that as well.
Use the angular velocity.
Yeah, what's v at 5 seconds would equal omega at 5 seconds times r. And if you take this omega right here and multiply it by r, 21.4 times 0.35 meters, you should get the same answer of 3.7.
You don't.
We don't?
No,
What did we mess up?
Radians.
Delta x over delta t is average velocity. Yeah, no.
What's the velocity at 5?
See? My-
Instantaneous.
Yes! That's correct. This is the average velocity. Whoa, good point.
He was right.
Very velocity between 0 to 5 seconds. So let's see if this works out. Then this velocity here ought to be the instantaneous velocity, right? At 5 seconds. Instantaneous velocity should be 21.4 rads per second times 0.35 meters. What does that turn out to be?
7.4. Yeah, that.
7.5. Okay, does that look right then? If this is the average, does that the instantaneous?
Seals to report to room 361.
But no, because the
Seals,
zero
please
doesn't
report to room 361.
All right.
7.5.
What was our velocity at 0? 0. Our velocity at 5 was 7.5. So what's the average velocity between 0 to 5?
not 3.7.
1.5.
1.5?
7.5 divided by
Oh, wait,
5.
No, not 7.5 divided by 5.
No. 3.75.
Average velocity is change in x over change in time. What's our, or if it's linear,
I don't want to.
if the velocity is linear and not changing as some strange function, then you could just take v final minus v initial and divide by 2, right? Which is what we have here. If you take 7.5 and subtract 0 from it and divide by 2, you get this.
Yes.
All right. So this is not our instantaneous velocity. That's our average velocity. So we only find our instantaneous velocity at 5 seconds when we use our instantaneous omega, angular velocity. Thank you, Mark, for spotting our mistake. Let's talk about rolling stuff just for a second. Okay, a couple of things about rolling. Number one is when something is rolling without slipping. So,
Oh yeah, that's good.
rolling without slipping. What's the velocity of this point right here when you're rolling without slipping relative to the ground?
0.
0. It's stationary. Okay, when something is rolling without slipping, when it rolls across a surface like this, okay, and it rolls across, notice that the point that's in contact with the ground is not moving at all. All it does is just come down, touch the ground, kiss the ground, and then lift back up. That's all it does. All right? That's all it does. Just come down, touch the ground, and lift back up. All right, that has a couple of major implications. Number one is you could consider this a pivot point if you wish. Okay? It is technically the pivot point about which the whole wheel is rotating. All right? So we could attack problems with that. The other thing that's important is, since there's no relative motion, no relative motion, that means that what kind of friction do we have at that point?
Static.
Yes, our friction is static. That means no delta x. So how much work does friction do?
0.
Work, remember, is F dot D, or F d cosine theta, but our delta x, or d, is 0. So the work done by friction is 0. So in theory, a rolling object should roll forever. Now, it does roll a very long time, but not forever, right? Objects that roll will move for a very long distance as long as the surfaces are smooth. If the surfaces are not smooth, what happens is that the imperfections of the tire or whatever it is rub up against the imperfections of the ground. And so there is a little bit of relative motion between the imperfections as it sets itself down and then picks itself back up. Okay? As each point on the tire does that. So we lose a little bit due to friction because of that each time the tire touches the ground, or everywhere the tire touches the ground. Okay? But in our imaginary physics world, in theory, things should roll forever if the surfaces are smooth. Okay?
Smooth.
Smooth.
Meaning no friction.
No, there is friction.
There is friction, that's why it's moving.
All right, now here's the other thing. That's a good question. I'm glad you brought this up. Our definition of smooth in the past has been if it's smooth, that then there's like frictionless, right? Yay, no friction. All right, but if we have no friction, will an object roll?
No.
No.
It'll just
So, this is this imaginary, we're kind of,
It's a paradox.
it is somewhat of a paradox. Without friction, you will not roll.
But when it's smooth,
But if you have a little bit of friction, when it's not too rough, then the object will roll.
frictionless.
Not frictionless, static friction, so therefore should roll forever. Because the static friction is necessary to give it a torque to make it rotate. Okay? Yikes. That's kind of weird, right? Now, you could try that. If you get out on a frozen lake and roll a bowling ball, it should slide. Okay? And actually, if you go to a bowling alley, it's nice. They've just waxed the lanes. You can toss a bowling ball down the lane. There's very little friction for a long period of time. And the ball will slide for a good distance before you start to see it start to roll. Okay? Now, let's take a look at what rotational motion looks like when you're rolling without slipping. What rolling without slipping really is the combination of two motions. This motion, where the object translates V, V, V. Every point on the object translates the same speed. Translation. Plus this motion, which is rotation. Okay? Stationary. Stationary rotation, where the velocity of the center is 0. The velocity of this point is this way at V, and the velocity of this point is this way at V. Okay? So it's rotating this way, right? So if I add those two motions together, straight translation to the right, and clockwise rotation, then what I get is this motion. The top moves at 2V. The center moves at V. And this point down here, velocity is 0. Everybody see that? This velocity plus this velocity equals 0. This velocity plus this velocity equals V. And V plus V equals 2V. And we get this velocity distribution that looks like that. Notice that the center of mass of an object that's rolling without slipping, this is rolling. Rolling, no slip. Rolling without slipping. An object that rolls without slipping is really doing these two things combined. And this point, when it touches the ground, is not moving. The center is actually, the center of mass is actually moving at V. Okay? And the top is moving at twice the velocity of the object. All right, this is omega. Now remember that omega is equal to V over R, where this is the radius. Okay? That means when you roll without slipping, because the way the math works out, that omega here, omega here, or the velocity of the rolling object, equals omega of the object of the object times the radius of the object. Now that's only true if you're rolling without slipping. If you are slipping, then this will not be true. Rolling no slipping equals this. So like a bowling ball, when you throw a bowling ball and it's sliding down the lane or spinning but not moving in the way it's spinning, like if you put a hook on the ball, then this is not true. Okay? Mark.
The no slipping part clears that.
Oh, the no slipping part cleared it up.
That's just weird because like, if a car's going 60 miles per hour, then the wheel would be 2V and 0, but then you said no slipping there.
Yeah, so what's really weird, if your car is moving down the highway at 60 miles an hour, that means the axle right here is moving 60. Now that should make sense, right? Your wheels have to be moving the same speed as the car, right?
Hopefully.
Does that make sense?
Yeah.
But the bottom of the wheel is not moving for that instant. Or every time, wherever the bottom of the wheel is, it's not moving. The top of the wheel is moving at 120 miles an hour.
So if I ever make it to 600 miles per hour,
That's
I'll be
right.
setting a world record at 12.
Isn't that weird?
You tell the police officers, at which point would you like to
That's
give
right.
me my ticket?
But officer, the bottom of my tires they weren't even speeding. They were sitting still.
I don't think that
And then he
would
says,
work.
well, I'm going to write you a ticket for the top of your tires then.
It's gonna be twice as much.
Your fine is double.
You go at 20. So you're gonna get 40 of
That's right.
10.
All right, let's see. No frictional losses, no work done. We'll talk more about that when we get to energy. All right, it's time to start working some real problems. Okay, here we go, my children. Our first rotational dynamic problem. Okay, I want to know what's the acceleration of the block. I want to know what's this acceleration. A equals whatever. Okay?
Is there a map? What?
This is a pulley. The pulley is pinned right there. Okay? So I have a pulley and I have a string and I have a mass attached to the pulley, attached to the string which is attached to the pulley. The pulley is free to rotate. We'll assume that the pulley is a disc. It's a disc pulley. Okay? And we want to know what the acceleration A is. So first of all, will the acceleration A be G?
No.
Will it be more than G or less than G? Less than G. All right. So first things first, will you please draw the free body diagram for the pulley and for the mass?
Cindy wants it to be monkey box.
What are all the forces on this mass? All right, we got an mg and we got a tension. Which one's bigger? Mg. All right, up here, how many forces?
So this time the pulley has.
The pulley has mass.
Okay.
Falling in free space. So.
Yeah, wait a minute. Whoa, 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 whoa. There has to be another force, or otherwise this pulley's in free fall. Okay, there is a vertical force from here upward.
Because it's
How big is that vertical force upward? Is it really?
tension plus mg.
There's another force. We got an mg as well. So I didn't draw my vertical force big enough, did I?
So V equals T plus mg.
Okay, let's do this, everyone. I would like for you to write F equals ma in the x direction, F equals ma in the y direction, and the sum of the torques equals I alpha for each one of these. All right, what does this look like for both of them?
0.
Okay, we got nothing and we got nothing. Okay, nothing for this one and nothing for this one. All right, sum of the forces in the y. What's that look like for this one?
V equals mg plus T.
Now, why are we able to do that? Where'd my acceleration go?
0.
Okay, we're assuming the pulley's not in free fall, right? It's stationary. So that's what we get. All right, what do we get over here?
T
equals
plus T equals mg.
T equals mg? Whoa!
Plus MA.
Yeah, we got an mg in here because this, and wait a minute,
T equals MA. Wait.
we got an acceleration here, right?
Oh.
Yes.
Oh.
So we've got an mg minus t equals ma.
And that's the A we're looking for.
And that's the A we're looking for. So let's circle that. That's what we want.
You can't see that.
You can't see that.
I can't see it.
I can't see it either.
There we go.
Green for go. We want that. Do we have enough information to find that?
Yes.
No, we don't know what T is.
I meant not yet, but we do.
Oh,
We
yeah.
will.
Well, couldn't we just plug T in from this? Would that work? No, we don't know what V is. Drat. All right. The sum of the torques equals I alpha. What's our torque? Oh, where's our pivot point?
In the middle, you said.
Ah, remember, pivot point, pivot point. All right, so how many torques do we have? One, because the other two have no radius. All right? So our torque is, and please remember everyone, when you're doing torque, R cross F. Always put the radius first, and the reason why is because you need to put it first because of the cross product, but also because the first few times through you have a tendency to forget the radius. You put the force, but you forget the radius. So always put your radius first, and then work backwards and find the force. So our radius, R, is R. And our force is T. And our radius here is R. T, and since it's a perpendicular force, sine theta is 1. All right, what's our moment of inertia? 1/2 mr squared alpha. There you go. What's our rotational one for the block? There is none. It's not rotating. So those are our three equations that we have at our disposal. Okay. We're still in trouble. Because if we solve this one for t and plug it in here, we have an unknown v. So all the things we don't know are underlined in red. And we're looking for this one. So I'll leave that one green. I seem to have too many unknowns. I have 4 unknowns here. Unknown, but we're looking for it. 4 unknowns, 3 equations. Drat.
There's 2 against the same together.
Math has failed me. Yes, it has, because I have 4 unknowns and 3 equations. That is impossible. Whoa, wait, whoa. We have 4 unknowns and 3 equations. You're going to have a part of your matrix that's blank.
Sure, why not?
Go away.
You failed. You've learned nothing. Bad. Okay. What do? We need another equation. Make up one. I like that. I choose to make up this one. The connector equation between these two is that A equals alpha R. Because we have no slip, right? We have a no slippage problem. Therefore, this is true that the angular acceleration of the outside rim of the pulley
Wait,
times the radius, that this point right here, I shouldn't do that, it looks like a pivot point. This point right here has the same acceleration downward that this object has acceleration.
Yes.
Does that make sense?
Yes.
That the angular acceleration of the pulley, that means that the acceleration of the pulley at any point is alpha times r. At the center, its acceleration is 0. At this point, its acceleration is alpha r, and that acceleration has to equal that acceleration.
In this problem, we don't keep the sine theta
Because it's perpendicular, so
Sine of 90 is 1.
sine of 90 is 1. All right, does everybody see that the acceleration of this point, and this point, and this point, and this point, and this point must all be the same? And so, therefore, the alpha here is related to A here by the radius r. So we have this magical equation in our radius, well here, let me leave it as it was, r, and so r's is going to be A equals alpha r. So I'm going to take alpha, that's A over r, and plug it in here. And what does that give me? It gives me RT equals 1/2 mr squared A over r. Now a magical thing occurs, very magical. Yoink, 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 all gone.
Yes.
And I get T equals 1/2 ma.
That's pretty.
It is pretty because now I can take that, plug it in here, and I get mg minus 1/2 ma equals ma.
M's cancel.
M's cancel, even better. So what's A?
G minus 1. Wait, no. Sorry. Wait.
I know it's at this point that we have algebra breakdown sometimes.
No. So that's 3/2 A equals G, so that's 2/3 G. Yeah.
2/3 G. Make sure you know how to get from here to here, because I will tell you that students will go through all of this junk to get here, and then they put down something weird like, yeah, G minus 1/2 or something. Put down something really odd, okay? There you go. Actually, what a lot of students will do is they'll put down 3/2 G, because they'll just do their algebra backwards. And 3/2 G cannot be correct, because the acceleration of this must be less than G. All right, there you go.
How do you know it must be less than?
Because it's not in free fall. If it's in free fall, the best it can be is G.
Yeah.
Or the largest it can be is G. All right. What would happen if I replace this disc with a hoop? Hoop.
Would it be a 1/2?
This 1/2 goes away. It goes away, goes away, and I end up with, if it's a hoop, A equals 1/2 G.
It's 1/2 G.
Now, whoa. If I do a hoop as opposed to a disc, why would that matter? Because the hoop has a higher moment of inertia. It's harder to get it moving, right? So therefore, it will descend slower. Okay? So that doesn't seem like something you want to do. Unless you want to store a lot of kinetic energy in it. Maybe that's what you want to do. A hoop will store more kinetic energy, rotational kinetic energy, which we'll talk about later. All right, so let's do another one. Here, something easy. What could be easier than a yo-yo?
Oh my god. Are you gonna make us find the period of how long it takes to go up and down?
Just let it happen. Just let it happen.
All right, don't make me mad. I'll make it a difficult yo-yo.
One that's raggedy.
One that is a sphere.
Yeah, a spherical. Consider a spherical yo-yo.
And we like those spherical flops.
Just because you're making me mad, I am going to make it a sphere. It's a sphere yo-yo.
Is it a hollow?
No, we can't do that because that's going to make it harder. Because how you can't wrap the string around the outside edge.
It'll go like this.
It
has a groove.
You can make it a hollow sphere.
It has a groove.
All right, so here we go. You want that, so we're going to do it. Yay. Here we go. Here's our spherical yo-yo. The spherical yo-yo has a radius of 2r, but the inside right here has a radius of r where the string is attached.
But that part is a disc.
Let's assume it's a sphere, a solid sphere.
Solid?
Okay?
Why?
There you go. We just made it fun. Because our other yo-yo was so lame.
I was happy with the normal yo.
Oh, you were happy with a normal yo-yo until you saw this spherical yo-yo.
I'm not thinking that.
This should run the spherical yo-yo. It would go like this.
That's right.
It's
It's called a ball of twine. All right. Let's say it has a mass of m. We'll keep that.
Can we do that and then assume it loses mass as it?
Oh, dude, that would
It could be
hard.
an integral.
It would be an integral because you have to know the rate at which the mass decreases. So you have to know the linear mass density of the string.
And then that depends on how fast it's going down.
Yeah, so its moment of inertia would change with time.
Yeah.
But at the end, it's nothing. It turns into just a string.
That's right. At the end, yeah, the yo-yo never comes back. It just turns into a long piece of string. I hate this yo-yo. It's so hard to wind back up. That's right. I dare you to do that for Christmas. You got some little younger relative and hand him a ball of twine and go, here's a yo-yo. And then you show them the calculus you did to figure out how long it takes for it to unwind. Someday you'll appreciate this. Go play with your yo-yo. My daughter would look at me and go, Daddy. That's how she would say it too.
That's how she would say it.
Like some. She's got that whole I'm a teenager thing down already.
Oh wow.
Oh yeah.
She's gonna be 30 then by the time she's
All right, here we go. Hey, sum of the forces in the x equals ma gives us nothing. Sum of the forces in the y equals ma in the y direction. Let's write that. How many forces do we have?
3.
3. I got an mg and I got a tension. Hey, are there any forces in the x direction? Are there? Are there?
No.
No. So when you unwrap a yo-yo, which way does it go? Straight down. Even if your yo-yo is this cheap yo-yo that I was talking about to begin with, like a roll of tape. Okay? Like a roll of paper. Let's not do tape because it would be sticky and it wouldn't
I'd be
unroll.
like, ah.
So if you had a long roll of paper and you held one end and let it drop, it would drop straight down. Because there's no side-to-side force whatsoever.
Unless you like walk the dog and you have to shoot it out.
Whoa, we could do the walk the
And
dog
then you
thing.
have the
It's not.
It's
Let's
not.
stick with the regular.
All right, here we go. What does this look like? Which way is it accelerating? mg minus t equals ma. That's the same one we had before. Sum of the forces equals ma. Oh, no, we did that one. The sum of the torques equals I alpha. Alpha.
I sub alpha.
All right, now, what does this look like? Hurry.
Oh, it's a fish.
Little tr equals
Okay, no, ready's first.
RT
RT equals
what's for the
I alpha. But what's our I?
Is the center a sphere too?
2/3 mr squared.
2/5.
2/5, yeah.
It's a solid sphere.
Yeah, why this is too late.
Okay, now look, here's all our unknowns. A, T, alpha, T. 3 equations, 2 unknowns. How do we fix that? Alpha equals A over R. Plug in.
And the tension's this way. Like this is your radius. Make it
Okay, here we go, and the magic occurs again. You ready?
down, straight down, which is parallel to radius. This radius is all around.
Are you keeping up? I think you're sleeping.
Wait.
I'm ahead of you.
Oh, here. mg minus 2/5 ma equals ma. M's go away. So what's a? 5/7. How do you get 5/7 out of a 2/5?
7/5. Or
It's
5/7
7/5
G.
and A equals 5/7.
All right, because
5/7
here,
G.
this is g minus 2/5 a equals a, or g equals a plus 2/5 a, which is 5/5. And so you get 7/5. When you move to the other side, you get a equals 5/7 g. There you go. All right, everyone. We have a 2 kilogram mass, we have a 4 kilogram mass, and uh-oh,
What is
our pulley, it has mass. Oh no. Now, I suggest everyone that you solve this with symbols first, and then plug your numbers in at the very end. I will give you this hint. If this is the free body diagram of my pulley, what are all the forces on the pulley?
2 T's, an mg, and 2 vertical, or 1 vertical.
That looks good to me. But wait a minute. Will the pulley rotate?
Yeah.
With it?
So what does that mean implication-wise for the 2 tensions?
One tension is greater than the
Thank you very much. One tension must be greater. Which one? One on the right. So I'm going to make this one a little longer. I'm going to call this one T2 and T1. Well, sometimes you might call them T left and T right. Actually, you know what? Sorry. In my notes, I did it the other way. T1 and T2. Sorry. Now, these are not the same tension anymore. Oh.
So they'll give it a different force.
And then this 4 kilogram. You've got an mg for it, and you've got a tension over here, but that's T1. And your 2 kilogram, you've got an mg, but you over here, you got a T2. And it's a disc. Okay, there's assignment number 1.
What?
Assignment number 2.
So what do you want
What do you
for?
want for mine, for us to mine?
Yes.
What's that?
What do you want to find?
What
What do I want? What?
What do you want us to find?
Oh, everything.
To solve for everything.
All right, I want you to find the tensions and the acceleration. So find T1, T2, and acceleration. So T1, T2, and acceleration. And just because I'm mean, angular acceleration. Haha. Oh, that's not even going to be any more work.